All right, ladies and gentlemen, this is going to be our next video on evolution and specifically looking at biogeography. Let's get started on our next video. So what I want to begin this video with is plate tectonics. So the thing that we have to understand when talking about plate tectonics is the land masses that we see today and where the continents are today are not where they've always been. Now, Pangaea is a geological landmass that existed when all the continents were joined and existed about 300 to 200 million years ago. Now, we can see this image on the left here is when all of the continents were actually collected in one giant landmass, and that's what we call Pangaea. Now, the question that we have to ask ourselves is what is going to go through and cause these plates to move? So if we look at an image of the Earth, and we're going to go through and slice the Earth in half, what we're going to see is we're going to see the crust, the mantle, we're going to see the outer core, and then we're going to see the inner core. Now the Earth's outer surface is made of the crust, and this is a cold, thin, brittle outer shell made of rock. So the crust is going to be relatively thin compared to the radius of the planet. And there are two different types of crust, and they each have distinctive physical and chemical properties. We have oceanic crust, and then we're also going to have continental crust. Below that, what we're going to see is the mantle. And the mantle is made of two important things. There is some solid rock, so it is made of solid rock, but it is also very hot. So, because it's extremely hot and because heat is flowing outward from it, heat is going to flow and create conduction and convection currents. And as this heat goes through and transfers all its energy to the atoms within this rock, it creates this semi-fluid layer. And we can kind of think as the convection in the mantle is very similar to the convection within a pot of water on the stove. So these convection currents are going to go through and rise, and they're going to go through and create this semi-liquid area moving in the middle of the Earth. Now, the inner and the outer core are at the center of the planet, and this is a metallic core that we go through and see in the Earth. And the density of the Earth's surface layer is much less than the actual density of the overall planet. So if we think about this, the surface layers are much less dense than the average interior of the Earth. Now, this is where the convection currents really originate, and this is what really creates the heat that goes through and gets pushed into the mantle and then goes through and pushes up on the crust. Now, the core is also going to create that magnetic layer that we will go through, and you may go through and look at in another environmental science course. So now that we've gone through and looked at the actual layers of the Earth, what exactly are plate tectonics? Well, a plate tectonic is a theory that the Earth's outer shell is divided into several plates, and they're going to glide over this kind of liquidy mantle and the rocky inner layer above the core. Now, the plates act like a hard and rigid shell compared to the Earth's mantle. So if we look at the diagrams here, we can see that there are all these different plates, and they're going to go through and move and shuffle themselves around because they're floating on top of that mantle. And we can see over time, we started with this large landmass of Pangaea, and as the plates have gone through and moved, we get the current continents that we see today. Now, the main driving forces that are going to go through and allow this to occur and allow the continents to separate are going to occur on these boundaries. Now, what we're looking at is a divergent boundary, and there's two other boundaries that you can go through and look at in other courses, but just for the sake of brevity here, we're just looking at this divergent boundary. So in the blue, we have the ocean, we have the lithosphere, and then we have the asthenosphere. We can break down layers of the crust and layers of the mantle, but again, we're saving that for another course. Now, along these mid-ocean ranges here, what we're going to see is magma. Magma from the mantle is going to go through, and it's going to rise through these mid-ocean ranges, or these cracks in the crust. Well, as that magma comes in contact with the ocean water, it's going to cool. And then more and more magma is going to go through and pile onto the lithosphere here. And as that goes through and occurs, it creates a force that is going to drive these two plates apart. So this is what is causing the continents to go through and move over time. Now, these plates are moving very, very slowly. They're maybe only moving about 1 millimeter a month, and that's about the rate that your fingernails are going through and growing on a daily basis. Now, we can actually see in the Appalachian Mountains, we can see how they went through and were formed. So Pangaea has been breaking apart for about 250 million years along these divergent boundaries. And the Appalachian Mountains were created by the collision of Eurasia and North America. And we can see in the image here, all of these ridge lines are created because of these plates going through, spreading apart, and then going through and colliding. So what does this have to do with evolution, and why are we going through and really learning about this? Well, if we look at this map, we can see that we have South America here, we have Africa, and we have Australia. And in South America, we have these birds called the rhea. In Africa, we have these birds called the ostrich. And in Australia, we have these birds called the emu. Now, if we look at all of these birds, they all look very similar, and they are all flightless. So if we look at the rhea here, again, very long legs, a large body, the long neck. Ostrich, the same thing. It's a little bit larger bird, but again, a flightless large bird with very long legs and a large body. And then if we look at the emu here, again, very similar shape. Now there are some distinct differences that we'll go through and look at, but again, all three of these birds look very similar. Well, if we look at this, we can see that the ostrich and the emu are roughly the same size. The ostrich is a little bit larger, the rhea is a little bit smaller. But looking at all three of these birds, they all look very, very similar. So what can we assume from this, and how did these birds go through and diverge and look the way that they do? Well, if we understand continental drift, once the continents separated, populations of the bird were trapped on their own islands. And I put island in parentheses here, and we'll go through and talk about why I did that. As time passed, the habitat for these three continents changed, and each population of bird began to evolve in different ways. Remember, continental drift is the gradual movement of the continents across the Earth's surface through geologic time. Now, if we look at this phylogenetic tree here, we can see that all three of these birds come from one common ancestor. And if we go back here, we can see, well, that makes sense. Morphologically, they look very similar. But we also see some key distinct differences here. The emu has these dark black feathers moving along the neck. Ostrich doesn't really have a large quantity of these feathers. It's much larger. And the rhea has this kind of black and brown pattern. So there are distinct differences, but we can definitely see morphologically that they are definitely from the same common ancestor. So the question that we have to ask ourselves now is how does this go through and occur? Well, all three of these individuals are different species, and the common ancestor used to live on Pangaea. Now, Pangaea, all the continents were connected, so this entire population could go through. It was all connected, so all the organisms could go through and reproduce with each other. Now, as the continents went through and drifted apart, what we started to see is distinct populations. And we consider this Gowanda and Laurasia two separate islands, and that's what I put islands in parentheses. What happens is there becomes a boundary that the populations can really no longer reproduce. So we can see the pink and the orange here. There's not very much contact for those populations to go through and reproduce with one another. This is what leads to a speciation event. And then as we continue and move on, and as the continents really separate, and we get to the continents that we have today, well, now we have these very distinct boundaries of the oceans. And because of that, we get three distinct populations with three different environments that each of those animals goes through and evolves to. So we can see now, in the case of South America, the rhea cannot reproduce with the ostrich and cannot reproduce with our emu because they're now on three distinct continents. And enough time has passed that they have become reproductively isolated and can no longer reproduce with each other because they've genetically changed just enough that they cannot go through and create offspring here. So what we can see from this continental drift is evidence that evolution has occurred over time, and the biogeography has played a role in how these animals have gone through and speciated. All right, so did you guys learn? Well, did you learn a couple of things? Did you guys go through and learn about plate tectonics? Did you guys go through and learn about the parts of the Earth and what really contributes to how the plates move around the globe? And then did you guys learn about how biogeography plays a role in evolution and how this provides evidence for evolution? This is going to be the end of the video. I will see you all in class tomorrow.